largely conceptual component. We're not solving equations any longer, but we are going to build up more stuff with quantum mechanics, and we're still going to do more stuff with Mathematica. Okay, so let's first talk about the Born-Oppenheimer Approximation. So this is really important for studying molecules. So it is supposed that the nuclei, being so much heavier than an electron, move relatively slow and may be treated as stationary while electrons orbit in their respective fields. And so ground calculations suggest that for every 1 picometer a nuclei will move, the electron will move by 100 picometers. Okay. So based on the Born-Oppenheimer approximation, we regard the nuclei as stable, as fixed. So there's some, center of mass, and there's some chemical bond bonding the two of them here, where this little orbit, right, that represents an electron orbiting some nucleus, and they're bonded together. And based on just how rapid the motion of those electrons are, we treat the nuclei as stationary. Okay? And so this leads us to the Lennard-Jones Potential Well. So I talked about this in the historical context. And hopefully this is the shape of a curve that we've seen before. Our typical potential energy well. Okay, we remember from solving the Schrodinger equation for atoms, right, that E is less than 0 for all bound states. And that's what we see right here. So on this x-axis, if this is our internuclear separation, all right, which really is going to be describing, a simple diatomic molecule, this would be my R, okay? Then we know there's going to be some sweet spot corresponding to the equilibrium bond distance and equilibrium bond energy, right? So the depth of the well gives us the equilibrium bond energy as well as the equilibrium bond length. And what we can also conclude from this figure is as we go further and further away, we no longer have this perfect parabolic energy well like we talked about in the harmonic oscillator model, right? Remember, the simple harmonic oscillator model tells us we have this perfect parabola, right, where the wave functions take on these features and so forth, okay? Well, from this Lennard-Jones potential well, we still have some amount of a parabolic shape at the bottom of the well. And as we might expect, there's energy levels in that well that are very similar to the simple harmonic oscillator wave functions, and we'll build that up. However, as we go to really far distances, we have to accept that the bond will eventually break. The two nuclei will get far enough away from each other that their electrons are no longer interacting. They're no longer sharing their potential, right? So the bond will break. And also, it's not symmetrical if we move to the left of the graph, because if we move to the left of the graph, we're forcing those nuclei to be too close to each other. And they'll have the effect of wanting to push back, right? When we get this positive energy up here, so if E is greater than 0, I'll remind you that that is, if we think about back to our Chem 361 days, that would be a repulsive interaction. So those two nuclei would then force back to that equilibrium bond position, okay? And so what's important to note, I'm talking about two nuclei moving in and out of each other, right? And we just talked about this Born-Oppenheimer approximation where the nuclei are stationary. What we're really getting at is if I have my proton system here and my electron system here, this is for one nuclei, right? The position of this proton to this electron is stable. It doesn't change. And if we look at another proton and another electron system, the position of this proton-electron system is stable. And so now each of these make their own system, okay? And we can allow each of those to move in and out, the entire proton-electron system. So Born-Oppenheimer is all about looking at each individual proton-electron system, and that proton in the center of that system is stationary while the electron orbits.